Hello everyone, today let's take a look at QP89. I have a feeling this is going to be a long video because there's a lot of ways to prove what the expected value and variance are for the binomial distribution. And I'm going to try to go over every single one. This question here uses a lot of what we talked about in combinatorics for the binomial coefficient. And I'm mainly going to use stuff that we talked about in QP 37, 38, and 39, and even when we just did the linearity of expectation too. So x is a binomial random variable, which means it has this PMF right here, and it represents the number of successes in n independent trials, each with success probability p. Okay, so the first way we're going to solve this is going to make our life a lot easier, is just to realize that x is basically the sum of a bunch of indicator variables. An indicator variable is something that's just equal to 1 with probability p and equal to 0 with probability 1 minus p. And one indicator variable represents one of our independent trials, right? They're Bernoulli. So for instance, if I have n equal to 5 and I'm trying to find the number of successes out of 5 trials, well, the total number of successes that I get x is just going to be equal to whether or not I got a success in trial 1, whether or not I got a success in trial 2, right? All added up to trial 5. So if I get a success in trial 1 with probability p, well, then I have a 1 here. And if I get a success in trial 2 with probability p, then I have another 1. If I fail here, well, then that's going to be 0, right? And you get the idea at this point. So basically, x is just going to be equal to the sum from, let's say, j equals 1 to n of the indicator I sub j. Okay, so if I'm trying to find the expectation of x, well, that's just going to be the expected value of this sum right here. And we just showed in quantibus number 92 that if we take the expectation of a sum, it's just going to be equal to the sum of the expectation. So this is just going to be equal to the sum from j equals 1 to n of the expectation of I sub j. Okay, now we also showed in quantibus number 91 that the expected value of any of these indicators is just going to be equal to p. So we can just rewrite this as the sum from I equals 1 to n of p, so that's just going to be equal to np. And that also makes a lot of sense because say we have n equals 100, so 100 different trials, and each of them have probability p, let's say 5%. Well, then I would expect that I would get roughly 5 out of them to be successes, right? Okay, so that's the easy way of getting the expected value, but let's actually get the direct sum later on where we're going to use the PMF and it's going to be a lot harder. Okay, now for the variance, this is going to be a little bit harder. Okay, x is just equal to the sum of the indicators, so we can just write it like this. Okay, now the absolute easiest way to solve this problem is just based on the fact that all of these i's are independent, and you know the fact that if you take the variance of the sum of a bunch of independent variables, that's just equal to the sum of the variances. And we haven't talked about that property yet. I'm sure we'll talk about it later when we talk about covariance, but basically the covariance is going to be 0, so we're just going to get that this is equal to the sum of all of the variances of the indicators. And then again, in quantibus number 91, we showed that the variance of all these indicators is just going to be equal to p times 1 minus p, and we're going to be summing n of them, so we're going to get n times p times 1 minus p. So this right here is the variance of the binomial, and this is the expected value. Those are basically the shortcuts for solving for these. However, we use that fact about covariance that we haven't proven yet, so let's just solve this using a different method. We know that this is equal to the expected value of x minus e to the x, all of that squared, right? And then in quantibus number 92, we showed that that is actually equal to this over here. And we already know the expected value of x from what we did up here is just going to be equal to np. So this is going to be equal to np all squared. That was pretty easy, but this is going to be the harder part. So the expected value of x squared is going to be the expected value of the sum of indicators squared. Okay, it started running out of room there, so I just cleared the page, but the expected value of x squared is going to be equal to the expected value of the indicator squared. And if we actually take a look at what the sum of the indicators times itself actually looks like, it's going to look like this when we expand it out. And if we start writing a few of these terms out, well, we're going to have I1 squared, we're going to have I1 times I2, we're going to have I1 times I3, and etc., right? And the expected value of x, again, just by linearity of expectation, well, that's just going to be equal to the expected value of all of these different terms. So the expected value of this one, the expected value of this one, etc. So now specifically for this term right here, the expected value of I1 squared, well, an indicator variable can only take the values 0 and 1. So when you square 0, you get 0 again, and when you square 1, you get 1 again. So that's not going to change, right? It's just going to be equal to the expected value of any indicator, which is equal to p. Now instead, for this term over here, the expected value of I1 times I2, well, these two trials are different now, and they're independent, we know. So the expected value of two terms, when you multiply them and they're independent, is just going to be the expected value of I1 times the expected value of I2. The expected value of any indicator is p, so we're going to get p squared. Now again, the expected value of I1 times I3 is just going to be equal to the expected value of I1 times the expected value of I3, again, because these are two different, so independent trials, and we're going to get p squared again. And you can pretty clearly generalize that whenever I get two variables that are the same, so I1 squared, I2 squared, all the way up to In squared, my expected value is going to be p, and when I get two different terms, so I1 times I2, or I3 times I5, or I6 times I7, the expected value is going to be p squared. So now this is just what we were doing in QP 38 and 39, right? We just need to count the number of terms in this expansion that are the same and the ones that are different too, and also the coefficients. Now for any term in this expansion, I'm going to be choosing one variable from this side and one variable from this side. So I have two different options. Now if I choose two terms that are the same, let's say I choose I3 and I3, then the number of ways to permute these is just going to be 1 because they are the same, obviously, basic multinomial. So the coefficient of the squared terms are all going to be 1. And now the number of actual squared terms is going to be equal to n, obviously, right? Because I can only have I1 squared, I2 squared, I3 squared, all the way up to In squared. So for our squared terms, we're going to have n, and they're all going to have coefficient 1, and the expected value for them is all p. So that's going to contribute n times p to our total expected value. And now let's do it for our different terms. So if I choose two different terms, let's say I1 and maybe I3, well, the number of ways that I can arrange these is 2 factorial, which is equal to 2. So the coefficients for all of the terms that have different variables in them is going to be 2. And now the number of total terms that have different variables, well, I have n variables, and I'm basically choosing 2 of them because I want them to be different. So n choose 2, right? So I have n choose 2 total terms where I'm multiplying different variables, and each of those have a coefficient of 2, and they all contribute p squared to our expected value. So I add on here n choose 2 times p squared. So this right here is the expected value of the sum of indicators all squared. And we can actually simplify this a little bit more if we expand out that choosing coefficient, and basically we're going to get n factorial on 2 factorial times n minus 2 factorial on the bottom here, and then we're going to get times 2. These are going to cancel, times p squared, which again we can simplify to n times p plus n times n minus 1 times p squared. So this is the expected value of x squared, but to get the variance, we also need to subtract off the expected value of x all squared. And we already calculated that. That was equal to n squared times p squared. Okay, now we're in the home stretch for this term up here. This is the expected value of x squared. We're going to simplify this. We're going to get np plus n squared p squared, and then we're going to have minus n times p squared, and we need to subtract off this term to get the variance, so we subtract off n squared p squared. You can see this is going to cancel here. And we're left with np minus np squared. We can factor out an np, and we get np times 1 minus p, which again is the variance. Now the actual hardest way to derive this shit is if we just brute force the expected value and variance using the actual probability mass function. All right, so here's the definition of expected value right here. Now the probability that big X is equal to little x in this case is our probability mass function for the binomial right here, which I plugged in. Now this is obviously going to be a really hard sum to calculate, but what makes it easier is if you notice that this is relatively similar to the formula for the binomial theorem, which we talked about in QP 38. Actually, we were using the binomial theorem a lot more than that back in combinatorics too, but this is basically the binomial theorem. You can see it looks very similar to this. The only problem is that we have this pesky x here, which is not here, and it's going to cause some problems. But what you do notice is that since our x and y values are basically p and 1 minus p, when you plug those in over here, p plus 1 minus p, it's going to simplify nicely down to 1 to the power of n. So up here, if we find a nice way to shift the variables n and x such that we maybe pull some type of constant out and we get it looking like this over here, well then we're going to get a really nice simplification, and that constant will just be our answer, right? So let's just find some way of doing that, right? Basically, first thing we can do is just expand out this binomial and see what's going on. So I'm going to have x times n factorial on x factorial times n minus x factorial, and then p to the x and 1 minus p to the power of n minus x. Okay, so we really want to get rid of this x out front, and you notice that we can cancel it with one of the terms in this x factorial down here. So let's do that. So once we do that, we've gotten rid of the x. We have this x minus 1 factorial on the bottom, but now we've kind of messed up our choosing function right here. What you do notice now is that if we factor out an n from up top, so we'll have n minus 1 factorial here, then when we plug those in here, they're going to cancel nicely. I'll show you what I mean. So what we can do is take out this n, and now we can do a change of variables up here. So for the n minus 1, we can just say, let's let y equal n minus 1, and then down here, let's just take another variable. Actually, I'll say, let's let a equal n minus 1, and then down here, let's let b equal x minus 1. Well, then in that case, n is going to be equal to a plus 1, and we're going to have x equal to b plus 1. So this is what it's going to look like. I've just plugged a in up here, I've plugged b in down here, and then I've plugged in both x equal to b plus 1 and n equal to a plus 1 down here. And when you notice that when we do that, we're going to have a subtraction, and then this plus 1 is going to go away from each of these terms. So this is just going to be a minus b factorial right here. And would you look at that, we both got rid of our x, and now we have a nice choosing term back. Now the problem is we switched using a and b, so we have to update both our bounds and these values up here though. So let's switch our bounds first. When x equals 0, we have b equals -1, right? So let's change this to be b going from -1, and then when x equals n, we had b equal to n minus 1. So this will go up to n minus 1 now, which is also known as a up here, right? Now when we have b equal to -1 and we choose a negative number, well, this term is going to be equal to 0. So that whole first iteration will be equal to 0. So we can basically just start this at 0. If that doesn't make sense to you, well, back at the beginning, we could have just canceled out this whole first term when x is equal to 0, because then the first term of this would have been 0 as well, right? So now finally, let's just change this one up here. We know x is equal to b plus 1, so we'll plug that in right here. And we know that x is equal to b plus 1 again, so we'll plug that in here. Now look at how close we are to having this look exactly like the binomial theorem formula. So right here, you notice one difference though. We have p to the power of b plus 1, and up here we have x to the power of k. So let's just factor out one of these p's, right? We can just make this equal to p times p to the power of b. And p is a constant, so we can just bring that to the outside over here with n. So we have p to the power of b, and then out here we can have n times p. Now also one more thing, I forgot to get rid of this n right here. We know that n is actually equal to a plus 1, so let's plug in a plus 1 for n, and then up here we get a plus 1 minus b plus 1, and again, these 1 terms right here are going to nicely cancel, and then we're just going to be left with a minus b up here. Now look at that, once we did all that changing of variables, now we have exactly the right-hand side of the binomial theorem up here. However, in here we have our x and y values as p and 1 minus p. We already talked about this. This right here is going to be equal to, if we plug in p and 1 minus p, we get p plus 1 minus p to the power of n times np. Now the p's cancel in here, and we get np times 1 to the power of n, which is just equal to np. So that's how you get the expected value. Okay, so that's the hard way of deriving the expected value. This might be my longest video, but now we have to do the hard way of deriving the variance, which is going to be even harder than this. Okay, we know that the variance is equal to the expected value of x squared minus the expected value of x all squared, right? And we just calculated this term. It's going to be np all squared. This is equal to n squared times p squared. So now all we have to find is the expected value of x squared. Okay, so the expected value of x squared is just going to be equal to the sum over all possible values that x squared can take times the probability mass function. And now the problem is not just an x, it is an x squared. So it's going to be a little bit harder. So we want to get this right here to look like the binomial theorem because it's already pretty close. And then we can do the same thing that we did before. But now how are we going to get rid of this x squared? Well, I'm going to somehow want to cancel it with this x factorial in the bottom of our choosing formula, right? So obviously x factorial is just going to be equal to x times x minus 1 times x minus 2, etc. all the way down times 2 times 1. And this is the only thing that we're going to be able to cancel the x with. But now if you notice, if we take these terms right here, right, this is equal to x squared minus x, and then that's going to be times x minus 2 factorial. And look, here is the x squared that we can cancel with, right? So how do we get this to actually look like x squared though? Well, let's just take x squared minus x and let's add back on x, and that'll be equal to x squared. And this right here was just equal to x times x minus 1, right? So if we let our x squared equal this equation over here and we plug it in over here, well then we're going to get this. And once we plug that in, we can just distribute this. We can use properties of addition and break this up into two different sums. And then it's going to look like this, but thankfully we've already calculated what this is with the expected value, right? This was just equal to n times p. So now all we have to worry about is this side, and it's going to cancel a lot nicer with this x factorial when we put it in terms of x times x minus 1, right? So now I've made room, I've gone into my 5th page. This is definitely going to be my longest video ever. But now that we know that this term is, we just have to solve this one more, right? And we can cancel these out and we'll get an x minus 2 factorial on the bottom now instead. So now let's just do another change of variables. Okay, same strat. Let's let a equal n minus 2 this time. That's just so we can end up with a nice cancellation down here. And then let's let b equal x minus 2. So once I've done that, I've pulled out the first two terms of this n factorial and I've replaced it with a. So this actually should be a factorial here. And then once I plug in n equals a plus 2 and x equals b plus 2 down here, I get the nice cancellation and I get this. So this is just going to be a choose b right here. Okay, now let's do a change of variable on our iterator. We have x going from 0 to n. When x equals 0, we have b equal to -2. When x equals n, we have b equals n minus 2, which is also known as a. So we have a up here. Now also, sorry, this should have been n minus x, not x, but when I have b equal to -2 and I plug it in here, I'm going to get a whole term of 0. Same thing for -1, so we can just increment this to 0. Now x was equal to b plus 2, so let's plug that in here. We have n equal to a plus 2, so let's plug that in here. We have a plus 2 minus b plus 2. These are going to cancel, and we're just going to be left with a minus b up here. Now x was equal to b plus 2 as well, so let's plug in b plus 2 right here, and then we want it to look like it is up here. So let's take out p squared from here and move it to the front. Now finally, this matches exactly the form of the binomial theorem, right? This is equal to 1. We've already shown when we plug in 1 minus p and p, we get the p cancellation, and this is going to be equal to 1 to the power of n by the binomial theorem. So now this is just going to be equal to this term up here. Okay, so now finally I've calculated everything. Let's hope I calculate it right so I do not have to redo this. But basically we have p squared times n squared here, and then we're going to subtract off a p squared n, and then we're going to add on the np for our other term, and that was just equal to the expected value of x squared, if you remember. But if you remember, for our variance, we also had to subtract off this term right here, which was equal to n squared p squared. So let's subtract that off right now, and then this will be equal to the variance of x, and that should give us our final answer. So it looks like I did it right. These are going to cancel right here, and we're going to be left with np minus p squared n, and then we can factor out an np, and then we're going to get 1 minus p, and look at that, that is our variance. Okay, so that was a ton of different ways to derive the expected value and variance, and in every single step we used something that we'd already learned, or we used a lot of stuff that we've already learned, right? So it was a good problem.